Welcome back to the workshop. We want to continue taking a look at section 2.1, set operations. And in our last video, we discussed several set operations. And what we'd like to do now is take a look at some examples where we're actually looking at Venn diagrams. So I think that you're familiar with Venn diagrams. Of course, if I wanted to give a quick example, I could refer to, right, we have a universal set when we're drawing a Venn diagram. So our box represents our universal set U. And then in our universal set, we have subsets. We might have subset A. And if we wanted to refer to subset A in our Venn diagram, then that's what we would shade in. So this represents our subset A. And if we wanted to, we could also have some subset B as well. And then not having that area shaded in would say that we're not referring to the subset B. Okay. So for our first example, we just want to include a few Venn diagrams which represent the basic set operations that we've discussed so far. So we have the union. So let's take a look at that. So if I have two sets, A and B, in my universal set U, then the union of them is the collection of items which are in A and in B. So I shade it all in. Now you'll notice that once it's shaded, it's shaded. It doesn't matter that I've shaded this region twice. It only contributes once to the union. So this is A union B. So the things that are in here are still only listed once if we were to list out all of the items in the union, or all of the elements in the union. All right. So let's say we were to consider the intersection. If I wanted to look at A intersect B. Again, this is my universal set. And I have two sets, A and B. Then their intersection is just what they have in common. So I would be shading the region that they have in common. That region. Easy enough. All right, we also have the difference of sets A and B. So I could take a look at our universal set, set A, set B, and I want to look at the difference, A minus B. This would include all of the elements that are in A, but not in B. So that would correspond to the region that is inside of A, but is not inside of B. So I get all of this, but none of this, because this portion of A is also in B. So this is A without B. Again, so far, these three operations can actually be done without reference to the universal set. It does not matter that we're working in the universal set. When we are working in a universal set, we have a definition for, or an alternative way to describe set minus or difference. All right, and the one set operation that definitely does need the universal set, what set are we working in, is the complement. So if I have some set A, and I want to look at a complement, a little nicer here, a complement, then I would be looking at everything that is not in A. Everything that is not in A. There we go, pretty straightforward. So that is Venn diagrams. All right, let's take a look at an example where we draw a Venn diagram. And we want to construct a Venn diagram that represents this set. So we've seen the basic Venn diagrams: union, intersection, difference, and complement. And what we want to do is we want to use these basic operations, these basic examples, to help us construct the Venn diagram for this set here. And to do that, we're going to essentially do one operation at a time. So by parentheses here, the parentheses say that we need to take B and subtract C first. And then once we've done that, we can union it with A. So we need two things here. So what I'm going to do is I'm going to first do, I'm going to first do A, just so we can see what A looks like. So this is set A, here is set B, and here is set C. Okay, so of course A is everything in there. Excellent. So that is set A. So I draw that just so that way we can see what it looks like when we have the interaction of three sets. All right, now let's take a look at B without C. So B without C, we've got so I'm working from left to right here. So I have written this diagram, and now I've written, or I'm drawing this one. So I've got A, B, and C. And of course, let's label them. If I want to look at B without C, I'm just shading in B, but not including the area where C is. So I get that region. So first I drew what A is. Now I did one operation to show what B without C is. And now I can use one operation, right? I can draw what happens when I union them. So that gives me the full picture. So below that, if I wanted to, I could draw some arrows to say that these two are combining to give me this third diagram. And that would be good. As long as what you're doing is pretty clear, then exactly how you show your work doesn't matter. But you should show basic operations. So if you did B without C and then A, let's see here, A union B without C, that would be okay too. Skip out this guy, but I thought that would be helpful in this case. All right, so we want our three sets, A, B, and C. And we have set A. And we also want to include with this the set B without C. So I'm going to include with that B without C. Excellent. There we go. And that's it. All right, so this is A union B without C. So I've constructed the Venn diagram by considering two smaller ones. Right, so I build up to the Venn diagram that I'm interested in. And that's how I can show my work. All right. So in this example, what we want to do is we want to simply use the theorems that we have discussed in this section. So that was, I believe, in our last video, we took a look at a couple of theorems. Right, there's a lot going on here, and this is what we want to use to simplify the expression, or the the expression, the joining, or whatever you want to call it, of sets that we have here. Okay. So we have A union, and we're taking A union B complement. So there's quite a bit going on here. All right, so we start off with A union B complement. All right, so the first thing that we can do is we can use De Morgan's law to rewrite this as A union. Now, A union B, all of that complemented according to De Morgan's law. Let's see what that says. De Morgan's law, A union B all complement is the same as A complement intersect B complement. So let's go ahead and replace this thing with A complement intersect B complement. So we have A complement intersect B complement. So De Morgan's law says that when you're complementing a union or intersection, you then take the other operation. So our union becomes an intersection, and you're just taking the intersection of the complements. All right. Now what we can use, well, let's make a quick note here. That was De Morgan's law. All right, and then we have that. Let's see here. Okay, the next thing that we have is the distributive property. So when we have a union over an intersection, we can distribute that. So that is the distributive property right here. We are taking an intersection over a union, so we can distribute that intersection to each of the following two parts. So we've got that this is equal to a union, a complement, intersected with a union B complement. All right, and that's the distributive property. Excellent. From here, A union A complement gives us the universal set. So that is U intersected with A union B complement. Right, if we take everything in A and union it with everything that is not in A, we get everything. Excellent, and that is that's from theorem 2.1, and it's part E. So we could look back up here. It is part E of theorem 2.1. I suppose that's 2.1.1. There we go. And then, this last step, I don't know that we have a good place to refer to for a theorem, but I think that it makes sense. So if we go back to here, A is a subset of A union B, or A intersect B is a subset of A, right? If we think about what's going on here, when we have subsets, so this is where I want to look, but I'm not sure that they really do me much good. If I take A and A is a subset of B, and I take A intersect B, then what I'm going to get is I'm just going to get A back, because A is a subset of B. So when I intersect them, if I have B and I have A, when I intersect them, I get everything that's still in A. So when I come down here and I take the universal set intersected with A union B complement, what I get is exactly A union B complement. And this is since A union B complement is a subset of the universal set. Okay, so that's what we want there. And just as a quick demonstration, I'd like to show that we can actually find this by referring to the Venn diagrams. So in red here, I'm just going to add this because it's not needed, but if you'd like it, actually let's put it in black, less seem like I'm doing something that you don't need. So this is worth observing, so maybe black is good. What we can do is we can create this, okay, using Venn diagrams. So the first thing I might do is I might take A union B, since I want to find the complement of that and then intersect it or union it with A. All right, so this is A union B. Then the next thing I might do would be take its complement, right? Because I'm going to construct this set. So I do one operation at a time, A union B, then take its complement. So A union B complement is everything that's outside of A and B. So I get everything that's outside of A and B. And now, one more step, I go ahead and union that with A. So A union B being complemented. So let's look at that. So I have A, let's draw A little bit smaller. That's better. And B, that looks good. So A and B. So what I'm doing is I'm taking everything that's outside of A and B. This is my A union B complement, right? And then I'm coloring in also A. So this is A union, right? This is, in fact, a union B complement. Yeah, there we go. Which is what we said, right? This is A and B complement. Yes. This is A union B complement. That makes sense. So that's just a nice visual representation of that. All right, let's see. If we wanted to, I don't know that it's beneficial in this case, but once we recognize that it's this, we could also see that this is, let's see here, B without A complement. So I don't know which is more simplified, A union B complement or B without A complement. Right, both of them require two things to happen: take away A and then complement, or find the complement and then union. But either way you go, it is more simple than this expression. All right, so that's all that I have for now. We want to take one more look at section 2.1, just for one more definition and example. Should be a pretty quick video, and we'll be done with section 2.1. So I'll see you guys back in the workshop real quick.